This is Ryan Womack, data librarian at Rutgers University Libraries in New Brunswick, and this is the recorded session for R for data analysis, a tidyverse approach. And I'm going to pick up where the previous introductory video left off and start out by just reviewing the websites that we need. The previous video, the intro video, will be the place to go if you need discussion of R, discussion of how to install R, those kind of things. I'm assuming right now that you're starting this session with a functional RStudio and you're ready to go with R for data analytics. So I'm going to use, and again, I'm just going to put the notes up in the top right so that you can see these web links a bit more easily. They'll also be in the code down in the description down below. And I'm going to go directly to the GitHub site. And once again, this is where the code for this session is going to, this session and future sessions resides. You can click on the green button to either download the zip and just download it to your local computer, unzip it, and you'll be ready to work with the files there. Or if you're a Git user, you can do something like the following. So I'm going to change to my R directory, and I'm simply going to copy this link, and I'm going to say git clone and the link. This is the easiest way to grab all the files using Git. As I mentioned earlier, we're going to schedule a Git, very basic Git session later in the semester as well. So now you can see if I go into the directory for tidyverse approach, I have all of those files from this site that have quickly been grabbed and put in this environment. So you can have R installed on your own system, RStudio installed on your own system. I will mention one other way to get to R, which is rstudio.cloud. rstudio.cloud is well named because it is a cloud version of RStudio that is provided by the RStudio people. I've already signed into mine. You can create an account that gives you 15 hours of free usage per month. It has become a subscription service where if you need to use more than that, you do have to pay for that. But as a place to play around and experiment, it's an easy way to get started. And here, if I wasn't logged in, you'd get a login screen that has a link to create an account. It's pretty straightforward. You can connect it to your Google account or GitHub account, or create a custom account just for RStudio Cloud and log in there. If you need to do that, pause the video and come back. And if you're using this method, then all you need to do to grab the materials is to say new project from Git repository and put the full URL to the Git repository in here, and it's going to do something like the following. It's going to deploy the project, and then you'll see in a moment an RStudio environment will pop up that contains all of those files in its directory. So this is a quick way, And again, one thing that's great about RStudio is that the interface is the same no matter what platform you use it on. So this is going to look the same as when we're on our system. But I'm not going to use RStudio Cloud for my own demo. I'd rather just use my own system. So I'm going to actually go back to my workspace, and I'm going to delete this project so that I don't use hours from my account. And I'll just close that. Okay, so before we launch RStudio for real, I'm going to go to this file that says R for data analysis.md, which we saw in the intro if you looked at that. And down at the bottom, there's this question: what is the tidyverse? Right? Why are we calling this the tidyverse approach? Okay, so R has been around for a while, and R has all these features that do data analytics. What happened? Why do we need the tidyverse? Well, tidyverse describes itself as an opinionated collection of R packages designed for data science, which share an underlying design philosophy, grammar, and data structures. So one thing about R, because there are many packages coming in from many different places, is it tends to be less consistent than you might expect. And now that there are 15,000 plus packages, it is harder to get started or know where to start in R than it used to be. So tidyverse has come along. These are packages designed and basically led by RStudio people who are the main developers for the most part. Although it is like any other open source project, there people can contribute from various places. This gives you a set of packages that'll do a lot of your basic data analysis and are designed to work together nicely without, sort of special munging that you sometimes have to do with other things. Also, there is great documentation, which we'll see, and because it has become quite popular, you'll see a large community using these approaches. So for that reason, I'm going to introduce R with the tidyverse approach, not saying that other approaches, including base R, are not worthwhile. Those are also worthwhile. But to start with, I think this is a good way to look at things. And the website, tidyverse.org, actually has documentation on all of the major packages in a very consistent way, which I'll refer to that as well as we go through. Okay, so now I'm going to launch my RStudio, and this is I'm running this on a Linux system. There's a little bit of a quirk on my system, which I have to adjust a command to disable the GPU acceleration before I run RStudio. Otherwise, I'm prone to have crashes. So if you're wondering why am I doing that from the command line, that's what I'm doing. Okay, so I have now my RStudio interface, which I have customized, and you can customize everything here by going under the Tools, Global Options, and changing the appearance. You can change how the code is highlighted, the types of fonts that you're looking to use, and the look and feel of the whole thing. I tend to prefer this kind of dark background, but you have all those options. You can also, in RStudio, you'll notice that there are these quadrants or panes, they're called, in the view. These can be customized and moved around, and you can customize what displays in those quadrants. So it's all up to you how you'd like to handle that. I've stuck with the default quadrant arrangement here, though. And unless I have a code file that I'm working with, I actually start in this, what's called the console in R, which is just a bare bones terminal that we can interface with the computing system. Now you'll notice here it starts with, I'm running R version 3.5.2. That's because I'm running a kind of a older stable version of Debian Linux. And although the new version, R has moved on to version 4, on this particular computer, I'm just being a laggard for now. So you'll see that. These starter messages can also be customized, which I might mention a little bit later. But let's stick with the basics here. I'm at the console. It's got a blank blinking cursor. What do I do at this point? Well, I can actually use R as a calculator. I can type things like 2 plus 2, 2 times 4. Whoops, sorry, that's a plus. Square root of some number. I can get some large numbers, 2 to the 300th power. And you can see this is the sort of interactive nature. What I type something and I get a response. Now, the strength of R, however, is when you build up a code file and you actually have a very systematic, structured way of working through your data analysis. Although R captures the history of your commands when you're typing in this form, a code file is going to be a better approach. So I mentioned the history, and you can actually see the history by going up to the top right and clicking on the History tab up here. You notice this is actually just the commands that I've typed. It doesn't record the output, however. We're actually going to talk about how to grab the output a bit later in the series, because the way to do that most effectively is not in this basic mode. Okay, so we want to actually work with a code file. How do I do that? Well, my bottom right window down here is set to the Files tab. I've set my default directory to be an R directory in my home folder. It's probably a good idea for you to leave your data projects, separated in some way like that, and not mingle them in with other files on your system. And so I've got some things that have been installed in my R directory, one of which is the Tidyverse Approach directory. So this is the place, no matter how you've downloaded these files, you just manually downloaded them on your system to some place, your desktop, your whatever, or you've cloned them, or you're working with them on the RStudio cloud. Just go to that directory and you should see the files here. Now we are going to use this file, R for data analysis.r, for this particular session. And any file ending in a .r like that, a capital R, is considered to be an R code file. There's nothing special about these files. They are just text files. You can create them with any text editor and they will run. And a lot of systems, like if you're used to just clicking on a file and having your computer know what to do with it, that's probably not going to work the first time you do it with something like this. You're going to have to get into a program that understands R, like RStudio, or change your computer settings to link the R files with the program or RStudio or something like that. So yeah, sometimes I've had that question where people just can't get the file open because they're not used to they're used to the computer making the linkage for them. That sometimes doesn't happen, and the way around that is to go into your R environment. Here we're using RStudio, and then open it from there. Okay, so you'll notice what happened is now my additional pane or quadrant of the screen has opened up as a code analysis up here. And my console has been squished down into the bottom left. So we're going to live like that for a while. I'm going to make the right-hand side a bit smaller so we have more room to see these things. And this is a great thing about the RStudio interface, is you can customize all that. If I'm just working on typing code, I can click this little window, sort of large window icon, and I can toggle that window and make it larger. I can toggle it again and shrink it back, or I can minimize it, and now I can see all the console. So I want to really see my results. I can just, toggle back and forth really quickly, those things. But for right, I'm going to try to stick with the split view for as long as makes sense for this session. Another thing, just we're going from the basics, is that if we want to write a comment in our code file, we start with a hashtag symbol, or what used to a long time ago on a phone be called a pound symbol. And that means if we type that like down in the console, if I type hashtag 2+2, well, nothing happens. You'll notice that it just returns me to a blank cursor, because that's now a comment that doesn't run as a computer command. Nothing that starts with the hashtag will run as a computer command. So, however, it does accept the input and just kind of return us back to the empty blank line. This is the nature of R, is that it's not going to tell you much about what it's doing unless there's output or unless there's an error. Now, if there's an error, you'll get a warning of the problem. And we'll see an error pretty soon. So I've tried to comment my code in a basic way. When you write your code, this is a good practice to explain what you're doing. And what I've done here is very basic commenting. But that means that line 9 is the first line of actual commands to run. And I'm going to start out by just typing the commands. And then I'll explain how you can speed that up a bit. So on line 9, the command is getWD. So I'm going to just type getWD with parentheses. If I type it with a capital G, you'll see this is what an error looks like in R. It couldn't find that function. And so we know there's a problem. That's not going to run. You'll notice also as I typed, this is a feature of RStudio, not base R, that it gives us a prompt. It starts to tell us, hey, we see you're typing GETW. Do you mean get WD like this? And then it even has help to explain what that function is. And we can press F1 to get additional help if we want to. So RStudio has this sort of feature that'll help you learn and remember the commands as you go through. But now we know that actually we should be typing a lowercase getWD. And what that shows us is actually the working directory. So getWD is just shorthand for get working directory. And it'll show us that we're now sitting in my R directory. So one point here is how the errors work, how the built-in help prompts work, and also that R is case sensitive. It is variable names, command names, all case sensitive. If you're not used to being careful about the case, you'll learn once you start using R. Another thing is if we look at line 11, getWD, if we type it without parentheses, what happens is we get information returned to us that's a description of the function. Now this is a little bit sort of internal, kind of computer readable, not human readable code. But we'll see another example of this in just a moment. Also, what the parentheses basically mean is to execute the command with the default options. And we'll understand a little bit more what that means in a minute. Okay, so now we're up to line 13. We've already seen this in action. We can use the console as a calculator. And we can create our own function. So we've seen just one function in action, getWD. If I want to create my own function, now I'm on line 18 of the code, I can give the command a name, the function a name. I'm just calling it funky add. This is nothing special. I can name it, and you can change the name to be whatever you like. And what I'm saying is funky add is going to be a function of two things, of x and y. Now, if I'm going to move to copying and pasting this information, just to avoid any typos. And I'm going to hit enter. And you'll notice something else happen down here at the bottom left, that what used to be a greater than sign has converted to a plus. That plus is a sign that we didn't type a complete command into R. R is waiting for some additional input so that this command will make sense, so that it'll be complete, and we haven't provided it yet. So we have said we're creating a function of x and y, but we haven't said what the function is. The function itself has to be enclosed in what we call curly brackets. Those are living just up above your return key on your keyboard. And RStudio will actually complete the second bracket for you, because these always have to be parallel, right? If we open a bracket, we have to close it. Otherwise, there's going to be a syntax error. So here, and I'm just, to make it very clear, I'm adding an additional enter. And actually, in the original code, I have this spaced out so that what's inside the brackets is separate. It's a little bit harder to type it like that. So I need to slow this down a bit, and I'm going to remove the second bracket just so that I can space it out the way I originally wanted to. Okay, now I type the function definition, and I'm just going to say x plus y plus 1, and I'm going to close the brackets. Notice these are all pluses on the left. But once I close the bracket, my cursor goes back to a greater than sign. And if I'm stuck over here in the history tab up at the top right, but if I look at the environment, you'll now notice that I have something called funky add in my list of things in the R workspace. Another way to list things in the R workspace is just a basic ls command with parentheses. And you can see I have funky add and I have q. Q is actually something I just have built into my system. You probably won't see that. You don't have to worry about the q. The funky add, right? So now it's a function. It's here. If I type funky add without parentheses, I get the definition of the function. And this is exactly what we have just put in. And so it's a function of x and y. It's defined by x plus y plus 1. And if I want to use the function, I can put parentheses. Now, if I type it like that, I'll get an error because I haven't actually provided what is x, what is y. There are also ways to define the default values of those numbers so that you wouldn't get an error in this case, but we're not going to worry about that right now. We're just going to put in some numbers. So if I say 2, 3, instead of 2 plus 3 being 5, it adds another 1 and it becomes 6. So this is a place where we can make 2 plus 2 equal to 5 if we want to do so. All right, so that's this very simple function. Maybe you think that's not a very useful function, but the point of making a function in R is that it's very easy for the user to create something that's on the same level as any other built-in R function with a command like this. And in between the brackets, you can put whatever you want. You can have very complex conditional tests for things that are going to set up the result this way if certain conditions are met. You can have all kinds of procedures all within the brackets. And this is actually the genesis of how our packages are created. They're like the interstellar dust from which the stars of packages ultimately form. People write functions. They need some stuff to get done for their work. They've got a few functions. They find that, hey, this is useful. It could be useful to others. And they move forward with creating that in a usable form for other people. And R makes it easy to do that. We'll talk about that in upcoming sessions, moving to that level. Okay, so I want to mention just a couple of other things before we get into the real data example. But I want to make it clear that R has lots of everything that you've ever heard of in statistics. R has it somewhere, either in the built-in or in a package, because R is the primary research tool for statisticians to develop these things, test them out. If it's been done empirically, you're going to find it in R. And so simple things like a sample. I want to create a sample or draw a sample of numbers between 1 and 100. And let's say I want to see 10 numbers drawn from the range from 1 to 100. Now you'll notice I typed that with a space instead of in the original code. It doesn't have a space. R is not terribly sensitive to spacing. Like I can really space it out like that, and it still reads okay and still executes the command. It is sensitive to case, as we saw. It is sensitive to punctuation. It is sensitive to closing out any brackets or parentheses. But spaces, not so much. Okay, so what happened? I got 10 numbers from the range from 1 to 100. And, there are lots of variations on this. If I say I'd like to sample just the numbers 1 through 5, but I'd like 10 of those, it's going to give me an error in this case. It'll hint at why. I cannot take a sample larger than the population. What it likes to do is draw each number once, and once the number is picked, it's no longer there. So if I sample 1 through 5 times, I'm always going to get each of the 5 numbers, but in a different sequence. And once I try to sample a 6th time, it's going to basically break because there's no numbers left to pull out. But you can see that it's told us that the problem is this option that says replace equals false. So I can change that option. So I can sample 10 times from numbers 1 through 5 with the option replace equals true. Just like that. And now it will, it pulls 1 out, but it puts the 1 back in. So it is possible to draw a number multiple times. And in this case, we drew 1 4 times and 5 3 times. And every time you run this, it's a random process, so you'll get a different set of numbers. So we want to find out, okay, we've seen a little bit. Okay, how do we know to use that option? We can access the help system in R quite easily by simply typing a question mark in front of any command. So if I say, what can I do with the sample? I can say question mark sample. And here's another case where RStudio is really nice, because RStudio, if you try this in other R interfaces or just the base R, well, I'll show you what happens. In just a terminal version, I say question mark sample. It's going to give me the same help, but it's all on one screen, and it's kind of in this not so nice plain text format that I have to scroll through. It's there, but it's not so ideal. Whereas in RStudio, the help appears nicely formatted, nicely out of the way in our bottom right window. Okay, so here's the sample. This is a function that does random samples and permutations, and it shows us the usage. So we sample X. X is, in this last case, is our 1 through 5. The size of the sample, our last example, we asked for 10. And we can say replace equals false or true. And we can say prob equals null. We can actually specify probability weights, right? So, for example, the default is an equal probability. But we could specify there's a 10% chance of getting a 1, there's a 20% chance of getting a 2, and so on for a custom probability draw. Also, we don't have to only sample numbers like we did in this simple example. You can sample from a list. You have a list of names, you have a list of addresses, places. You could sample from those and just get a random grouping from your data. So this is typical of an R function, that it has a very basic, straightforward initial use, and then you dig in the help. You try to figure out how the function works, what other things can be modified, and you can do more advanced things. And all of the help format in R looks a bit dry. It takes a little bit of getting used to, but they're all written in the same format. So once you get used to it, you're able to digest help from any package, essentially. So here we have this, description of how each argument of the function works. Sometimes there's a discussion of, details. So this does talk a little bit more about exactly how the replacement works and things like that. And down at the bottom, the very last part, you're typically always going to get some examples of using the code. So sometimes I'll just jump to that, say, I just want to see how a usable chunk of code to see how this works. That's in the help also. Okay, so we've seen an R function, but more importantly, we've seen the help that's accessible via the question mark. I'll also mention, just as another example of a statistical function, like a reverse norm. R norm is a random sample from a normal distribution, and the standard normal distribution has a mean of 0 and a standard deviation of 1. So when we just run R norm in a very plain form, we're going to see numbers centering on 0 and between mostly -2 and 2 typically. But we can modify that via the options. For example, in line 28, we can say mean equals 100 and SD equals 20. And in order to run this command, I'm going to start using my RStudio features a little bit more as I go through. I can highlight this and use the run button. So I say run up here, and it'll paste that whole line down below. And so now I've got some numbers that are centered on 100, and plus or minus 2 standard deviations away is where most of those results are going to lie. Now, if I do a question mark here, question mark R norm, you'll see the help I get is actually for the whole family of stuff we can do with the normal distribution. So it's a density of the normal distribution, the probability, cumulative probability function, the quantiles of a normal distribution, and a random sampling from a normal distribution. This is available not just for normal distributions, but everything. Poisson, Bernoulli, logarithmic, like everything that you've heard of. Again, you will see in R a function corresponding to it. And once again, the format of those that help is standardized. And if you want to see examples of some of these, you can go down to the end to see those examples. Okay, question mark is probably going to be the lion's share of the way you use the help will be via the question mark name of function. But you can also access the entire help system by going to this help tab on the right, clicking on the home, and you'll see there's resources for learning R. There are full manuals that are there for like an introduction, how to import and export data. And then particularly useful are the package references. Under reference, you'll see packages. And this is a list for each package. We can quickly get to the functions associated with that package. And also we can do a search across everything. So if we want to search for things that might involve a normal distribution, we might just search normal. Now, if you go on Google and you just try to search R, right, R is just a letter, so it's a bit of a pain sometimes to search for R help. I might search R stats and then like the name of some concept on Google. You can also, if you have a specific error message that you get, Google is great if you paste in that error message and then say R or R stats. That'll work. But often you really want to search within R itself. And so the search that's in the help is searching among all the functions that are installed in packages on your R system. Here are things that, in this case, mention normal distribution, so that's going to be a lot. But we can find out, all these things, right? So there's the normal distribution in the base stats package. There are also other normal models that are built into these other packages. And the first thing before the 2 colons is the name of the package. So there is stats package normal. There's also MGCV, MVN, so multivariate normal additive models built into this MGCV package, for example. So I encourage you to use the built-in help. It's in HTML format, but it's actually locally installed on your system. So even if you don't have an internet connection, you can access this help. And, it's, again, a little bit dry, but it works and you get used to it. And it's good to learn how to make effective use of the help. Okay, so now at this point, we're some ways in, and this may be a good point to break the video in parts so that the next part will start with using the data. So I'm going to break here, and I'm going to say thank you for listening, and okay, welcome back. This is again Ryan Womack, data librarian at Rutgers University Libraries in New Brunswick. And I'm just going to, this is part 2 of the data analytics, R for data analytics session. And I'm just going to jump right in without introduction because otherwise there's no point in making a part 1 and part 2 if we have to recap everything. So we are here in the middle of the R for data analysis.R file. And if you are confused by where we are, you need to go back to part 1 and look at that. But we are we've finished our introductory discussion of what R functions are generally like, and we're now going to talk about tidyverse packages. And here we need to install packages. If we have not installed things before, we have to install them, and you would do that via a command like install.packages in line 36. And I'm going to say install the tidyverse, and I'm going to install all the dependencies, all of the other packages that might be needed to make the tidyverse work. I'd like those too. Actually, you really need those for the tidyverse, because the tidyverse is really what's called a meta collection of several other packages. And if you don't select dependencies equal true, you will actually be missing a lot of the functionality. Now, I illustrated copying and pasting before. I illustrated using the run button. And you'll notice when I hover over this run button, the keyboard shortcut for that is Control-Enter. And I think that you might be like me. Once you get used to using Control-Enter in RStudio, that's going to be the default of how you run commands. So I would just put my cursor on a particular line and do Control-Enter, and then it will run that command. Now, I've already set up my system with the tidyverse on this machine, so it didn't have to pull in a lot of additional stuff. This step might take a few minutes for you if you haven't installed tidyverse before. So I would say, pause the video and come back when that's finished. You should see something like this, that it goes through some steps installing, that it gives you some confirmation messages that things have been successfully unpacked, and doesn't finish with any errors. If it says done and the downloaded packages are available, that's the kind of message you want to see. If you get an error message, what it sometimes means is you have to go back. Often the error message will have the clue of what you need. It'll say, missing package XYZ, couldn't install tidyverse. Then what you need to do is to run a command like install packages XYZ, or whatever is mentioned there. Run that first, and then go back and try to run the other install again once you've completed the missing piece. So often, there are too many dependencies among the packages to make everything completely smooth. There's some detective work involved sometimes in adding these other packages in. And you can always Google the error message that you receive when something doesn't install, and often there'll already be a page that describes what you need to do to fix the problem. This is part of the do-it-yourself nature of working with a complex network of open source packages. It's not quite the same as having one single stats program installed. Also, on your own system, it is a good idea to run what's in line 39, the update packages command, to run that pretty regularly to check your system if there are new versions of anything out there that you need to get. Because if you get too far out of sync with the latest versions, that's when it becomes really hard to patch your system without doing a complete reinstall. If you run update packages on a regular basis, your system will keep running smoothly. So I highly recommend that. Okay, the install statement, you only have to do that once on your system. Then you have the software on your computer. It's like installing Microsoft Word on your computer. But when you want to run the software, just like you need to click on Microsoft Word to activate it, in R you need to activate the packages. And in R we do that with the library command. That's on line 42. And I'm going to use Control-Enter from this point forward. So I ran the command library tidyverse, and you'll notice what it did. In this case, it's actually loaded a whole set of packages, because the tidyverse is an interconnected set of packages. That's unusual. Usually you're just running one at a time. But here it lets me know that it's loaded 8 things: ggplot, tibble, tidyr, readr, and these other packages. In the future sessions, we're going to return to these in a lot more detail. But this session is to kind of give you a basic example of working through data analysis. So we can get help on the tidyverse through the R system. But because there is this very nice website that we saw, tidyverse.org, I often, this would be the exception, typically the website is less informative than the packaged help within R often, but not so much with the tidyverse, because with the tidyverse we can get much more detailed browsable help. And there are things like these cheat sheets which provide a convenient reference to the sort of standard commands, the most frequently used commands, and those are also real helpful. They are true cheat sheets. They're not. They assume you already know how to use the commands, and they're just a memory aid. So don't be intimidated by all this if you see it for the first time, that you're expected to understand this. You've already learned ggplot, and then you use this as a reference. So the website itself has a lot of great information, not just the cheat sheets, but all of the full descriptions of each command are here. And it'll also link you to full books and manuals that have often been written about those things. So let me go back to my RStudio. So what we're going to do in this session is we are going to take, we're going to work with some live data. I always like to work with real data rather than a sort of toy file. And it'll be a little bit messy because it is real data, but that's my approach. I kind of prefer you to see that up front and think about how you might handle it. And the data manipulation part we're going to skim over, because that's going to be covered in more detail in the third session on data wrangling. We're primarily grabbing this data to illustrate how we'd want to do analysis on it. So I'm going to run line 52. This actually goes to the World Bank site and pulls a file that's on gender statistics. This is stuff that you learn about these files by actually going places like the World Bank site, and you look around and you figure out what format the file is presented in, and you figure out where you need to pull the data from. This is not an automatic process, just so you know, but I've done that sort of preparatory work for you so that we can pull this data in. We can unzip it because it did come in a zip file in line 53, and I have to give it a local name, right? So the local name I gave it when I brought it in was called gender zip, and now I've unzipped it. I can actually see it in my files, right? If I go to the files, the file folder, actually maybe it's just in my working space. I'll see some files appear once I have done a little bit more manipulation. Right now it's actually being sort of held in memory temporarily. All right, so the key here is once I've unzipped it, I have the CSV file, comma separated values file. And that's a very common, very plain, very compatible data format. We will talk in the future sessions about how to import from Excel and import from other formats, but right now this is just CSV. And I want to point out the difference between base R and tidyverse. So commented out in line 56 is the base R command. So normally with a CSV file you would say read.csv, and that reads the CSV into R and converts it into R data format. The tidyverse functions typically will use an underscore instead of a dot. So instead of read.csv, we have read underscore CSV. And It functions the same way. There's just some tiny differences, which again we'll get into in a later session. So on the right-hand side, now I've used this arrow a little bit earlier, but I didn't quite explain it. This arrow in R is called the assignment operator. And it's written by typing two characters, a less than and a hyphen, like that. It is symbolically representing an arrow. So the arrow takes what's on the right-hand side and puts it into the left-hand side. Now the left-hand side is just a name that I'm making up. It can be whatever you like. So I'm calling it gender_data. And it reads the contents of the CSV file and converts it into something usable by R. And when I hit Control Enter on line 58, you'll notice that it did run, and it gives us some feedback about how it parsed the information. So it's got a little bit of, as it says, missing column names. So we're going to see what that means in just a moment. So we got some warning. Often the warnings are not fatal warnings. They're just like letting you know to look out for something. You'll also notice that on the top right, we now have a gender data object that has 164,000 observations or rows of 66 variables. So that lets us know that, yes, something came into the R workspace. And there's even a browser built in. When we click on this play, we can get some more information about the data. What are those variable names? What does the data in them look like? And we can even start to, by clicking on the sort of spreadsheet looking thing, I can get a view of the data that's in a tabular type format. Now R is not good at really scanning lots of data. You can see not a lot fits on the screen here. It doesn't have terribly sophisticated filtering options, although that is improving with each iteration of RStudio. If you have data that is small enough to be sort of human browsable, you might want to get familiar with it in Excel first before you think that you're going to get a good view of the data in R. R is good for the automated functions that we're about to see. Now, a lot of data is so big that it's not possible to effectively human browse it, so that's something to keep in mind as well, that you may have to go straight to an R-type environment. All right, so we've imported the data. An important thing to know about how you can access the data is what's called matrix notation. So if we use square brackets after the name of the data object, first of all, let me just type the name of the data object. If I say gender_data and hit enter, what I get is I get a kind of representation of what the data is. It's telling me that it's a tibble, which is the tidyverse data format. Again, more on that to come in a couple of weeks. It is a matrix that's 164,000 some by 66. And here are the first 10 rows of data and a few of the variables, the ones that fit on the screen, right? It essentially in this view can only show me 5 of them. And then it just goes on to say, well, there's this much more, 61 more variables that have this arrangement. And you can see most of the variable names are the years. And there was something in the final column that kind of didn't come in correctly after 2020. That's X66. And we're going to kind of ignore that because that is not very significant for our analysis. All right, so that's a big matrix of stuff. If I want to just see pieces of it, I can use matrix notation. And so if I say bracket 1, 1, bracket 1, comma 1, that is the first row and the first column of data. So I just get the entry in that first cell that says Arab world. By the way, this data is for all the countries of the world, plus these defined regions like Arab world or Europe or places like that. Okay, now if I want to see a little bit more, I can say the first 10 rows and the first 6 columns. So I can indicate a range with a colon, just the same way we did in the sample command. And here's the first 10 rows. They're all about the Arab world, and the indicators are the variables that are being discussed. So we actually can't even really see the full indicator name, but there are things about what a woman's ability to do certain things are. A woman can register to vote, I think, like something like this, line 7 is my guess of what that one is. And then if there are data entries, which there are not for the early years here, those would appear out on the right. Now we can also omit a column by saying -1, right? So if I say first 10 rows and not column 1, that's what is going on in line 63. So you can see it starts now with the second variable, which is country code. And if I want to get all of the columns, I can just say comma and then nothing. Just leave it, not even a blank space, but just nothing there, and go straight to closing out the bracket. And now I have the first 10 rows, but all of the columns. And this is useful in various ways when you're doing your work. So now I'm going to start manipulating the data, and I'm going to move quicker through this without explaining too much, because it'll all come back in the third session. So I want to see the names, because that just shows me the variable names, and I'm not interested in the country code or the indicator code. For me, the country name and the indicator name are enough. I don't need to repeat that information in a coded form. So I'm going to drop that with the command in line 67. And now I'm going to check the names and just make sure that those are dropped. And we can see they are gone. My goal here is to create a very simplified extract of the data, and that's what the sort of next few lines of code take care of. For you to follow along, you have to really do every step here. If you can't skip, because it will be missing some piece that is required later on. Except that line 79 is optional. If I found that if you're on RStudio and you try to manipulate this larger data set, you might crash, you might run out of memory. So you could experiment on RStudio. I mean, when I mean RStudio Cloud. If you are on RStudio Cloud or a system with limited memory, you can reduce the size of the data set just by taking, in this example, the first 3,000 rows. But if you're not, then you don't have to run this line. Line 79 is optional. And I'm not going to run line 79 because I don't have that memory worry. All right, now I'm going to kind of swap the data around and filter it so that only the year 2017 is available, which I found looking at the data recently was the most recent years still have a lot of missing data because it takes a while for everything to fill in. So 2017 was pretty complete, so that's why I went for that. I'm going to pivot the data in line 82, and don't worry about what that does because that's coming up in the later session. I'm going to filter the data in lines 91 to 93. And this is using tidyverse style data manipulation. And again, I'm going to postpone the discussion of that until 2 sessions from now. And just clean up things a bit in lines 95 to 99. And in each step, I'm creating kind of a new, this is a general data practice that I like to observe is, I imported the data in one form. And every time I transform it, I rename the object to something else so that if I make a mistake or I want to go back, I always have that older one available. And I would really recommend you do that as long as you're not running out of memory on your system. Sometimes with large data sets, it's unavoidable that you're going to have to transform and overwrite some existing data because you'll just run out of space. R is, by the way, limited by the amount of memory that's available on your system by default. There are ways around that, which will be discussed in our big data series with using Amaral and R that's coming up. But the standard R installation is limited by the amount of memory, RAM memory that your system runs. So that's when I say run out of memory, I'm talking about run out of RAM. Okay, so I have now gotten what I wanted through these transformations, which is a data set called Gender Data 2017 Wide, and that data set focuses on the year 2017 only, and I have transformed it so that instead of the years in columns, I have all of the variables are different columns. And so each row is a country and each variable is a column. We can see that a bit more easily if I click on the spreadsheet view. And you can see that I have the regions and the questions that were asked on the top right and whether there's answers for individual countries. And so they don't actually compute that like yes or no answers for the regions, but they do get into that for individual countries. And of course, there's 627 variables here, so I'm not going to try to browse any further. But you can see, kind of get a feel here of what I've done with the data. Okay. Also in lines 101, 102, just notice that if you've read data into R, you can equally well write data out of R. So when we're working in R, we're in the R native formats. To make things usable to others, often we need to get it out. And so we can write CSV files, we can write Excel files. That's also coming back in a couple of sessions. All right. Now I can get information about my data set via a command like summary, and I'll let you run the 109 and 110. I'm just going to go straight to 111, which is the summary for the final version of the data set. And basically what that does is gives us information about every question, except that it doesn't really display that well on this screen. I can see that a bit more. I'll see that again in a couple of lines. So for right now, let's just move past lines 109 to 111. If we want to improve the way that it is summarized, there is a way in Tidyverse to do that, which is illustrated in lines 114 and 115. So we're going to take the gender data wide and pass it using this symbol that's called a pipe. And we're seeing that for the first time, or mentioning it for the first time right now. That's going to be a key to the data wrangling that we see in lesson 3, session 3. And so I take the existing gender data and then I summarize it. And then when I summarize it this way, I can specify what I'd like to see. So here I'd like to see the mean, and it will report only the mean for each of those variables. Except, once again, I've got this summary view, and to push the entire output into a table is something that I'd really want to do as a separate step. Okay, I'm going to also give you a caution, right? We've seen the ls function in action. The ls function now will have a few more things associated with it because we've processed these gender data files. If you want to remove things from your workspace, and I'll go ahead and remove the funky add because we don't really need that. I can just say rm and then the name of the object. And now it's gone from our list in the environment. It's gone if we try to list the function. Also, if you're not aware, a very useful shortcut is to use the up arrow, which cycles through the recent commands. So if you want to run something again and it's this long thing that you don't want to type, you just use the up arrow and it'll retrieve the most recent commands for you in order like that. So that's what I did just now to get the ls command back. But on line 119, this is my warning to you, is don't run line 119 unless you're sure you want to remove everything. If you want to remove everything from your workspace, you can list everything in your workspace with ls and then pass that list to the remove function. And the shorthand for that is like this in line 119. But don't run that. Don't run that now. It's a very dangerous command. You always want to sort of think twice before running any remove command, any rm command. Think twice. Make sure you really want to do that. Okay, so now we've got all our data ready to go. Now we really want to start studying it. And in this example, we're going to study a particular thing, which is life expectancy. So I'm going to look at the mean life expectancy at birth for women, and that is in line 123. So if I run that command in line 123, I can see that across all countries, this is a simple average, it's not weighted by population. The mean is 74.7. And how does that command work? Well, mean is obvious what that does. Inside the parentheses, we have this fairly long thing, which says, first it says gender data 2017 wide. That's the name of the data set that we want to pull the variable from. And then there's a $sign. I call this the $sign notation. After the $sign comes the name of the variable. So in this example, because we took the data straight from a live source, the variable names are quite long and they're not computer friendly because they have spaces in them and stuff. So we can deal with that by enclosing the variable name in a, not quite a quotation, but these sort of backward apostrophes, backtick marks, and that enables the computer to recognize that we want to look for that entire string. When you're creating your own data, I really would recommend simplifying the data names and using something like life_expectancy is a much more computer-friendly name that you won't have to escape in quotes. Or it could be female life expectancy is more straightforward. But since this simply read the column names in from the external data file, this is what we've got. And we do have to remove not available data in order to get an accurate count. Otherwise, we'll get an error. So we have to say na.rm equals true. That's the option to remove the not available data. If I don't say na.rm equals true, and I'm going to do that again. It's going 1. There we go. my answer is then going to be NA because it just can't deal with the missing data. So we have to remove the missing data before we take the mean. Now I can take a summary of this same variable. That's in line 124. This is when I said earlier, let's wait a little bit on what the summary does. We were trying to display too much data before, but the summary for one variable shows us this encapsulated description, descriptive statistics. So life expectancy, the minimum life expectancy for women is 54 across all countries in 2017. Median of 76, mean almost 75, and there are 18 missing data elements there. Whether those are countries or regions, we're not sure. Also the max 87.6. It also shows us the quartiles, right? So we get this sense of what that particular data item is about. So the summary command it's always useful like that. It gives you this useful information. All right, so I talked about this $ notation where we, in general, we refer to a data set. We might say gender life expectancy, gender $ life expectancy would be a simpler example for a different data set where we name the data set and after the $ is the name of the variable. R can handle multiple data sets at once. This is a strength of R. It enables us to mix and match things, and we don't have to merge data sets in particular in order for them to work together. So that's good. But sometimes it's a pain because we're only dealing with one data set, and we don't want to go around typing the name of the data set $ over and over again. We can get around that by attaching data. So this is line 127. We're going to attach the entire data set, gender data 2017 wide. And now we can simply ask for the mean of the life expectancy without the additional name of the data set $ prefix. So we can get the female life expectancy. We can get the male life expectancy, which is notably lower. It's just under 70. And we can get summaries of those two. So the third quartile of male life expectancy is very similar or is even below the median life expectancy for females. So we want to kind of understand this relationship in this example. We can visualize the data. Now, next session on ggplot, we'll do all visualization, lots and lots of visualizations. But right now, we're just doing a basic plot. And we plot one variable against another. So we say plot the name of the variable, which in this example is the long full description. And we use this tilde, or little squiggly symbol, to say plot what's on the left-hand side versus what's on the right-hand side. The tilde, if you're not familiar with typing that, lives up in the top left of your keyboard. You should be able to find it up there with the shift. And that tilde gets used a lot in R. We're about to see it come back again. All right, so this looks like what we're plotting here is on a country-by-country basis, right? It looks like there's a pretty linear relationship. If there's low life expectancy for males in the country, there's low life expectancy for females. Okay, this looks maybe like what we would expect. But we can also plot simply a 45-degree line on top of this graph, which is not going to quite look like 45 degrees because this graph sort of stretches to fit the space. If we stretch the window, we get something like that. Once we plot the 45-degree line on top, we notice that actually in every case, every country, the male life expectancy is lower than female life expectancy. All of the female dots lie above the line, which is what that means. This is another nice feature of RStudio, by the way, is that when you plot something, it just pops up in your viewing area on the right. It doesn't interfere with your code. on the left. Okay, so we'd like to study this question a little bit more. I'd like to compute the difference in life expectancy country by country. So that's pretty straightforward in R. I'm going to name the new variable in line 138. And I'm going to say this new variable is, using the assignment operator, once again, the kind of arrow, once again, generated by typing less than sign and a hyphen. And it's going to be defined by life expectancy for females minus life expectancy for males. And, this is the minus sign that does all the work. Again, I'm still enclosing those long variable names with spaces in tick marks so that I don't generate any errors. And, R operates sort of natively on vectors, on matrices. This is one of the really nice features about it. So even though I have this very simple form of the equation, which is essentially this life spread is female minus male, because each of those is a vector, it's going to automatically go element by element, and the results will be a list of the difference for each country. And once I have that information, I can do like I did before, see the mean, see the summary. So the minimum difference in life expectancy is 0.6, and the maximum goes all the way up to where women live 12 years longer than men. It's really quite a range. When we plot this new variable, the basic plot is just plotting the index that we see in line 141 is just each country, right? So the index it's probably alphabetical by country, and so it doesn't have a data meaning in a sense, which is why we see the plot scattered looking like that. However, we can plot against other things, like in line 142, we plot against GDP, or GDP per capita in constant 2010 dollars. So here we can see, okay, there is some pattern that for higher per capita income, the life expectancy differences are maybe not quite as extreme or as variable as they are for low. However, the places with the lowest difference are also low income. Is interesting. And I'm going to skim through 144 to 150 very quickly because R has a whole bunch of functions for descriptive statistics. They're very straightforward. SD for standard deviation, var for variance, median, quantile, etc. Just to, again, reiterate that if you don't remove the not available data, most of these functions are going to just break down. So if I say SD life spread, hoping to get the standard deviation, I get an error. But if I remove the not available entries, then I'll get a meaningful result in line 146. So I'm just running those. Here's the variance, here's the median, here are the quantiles expressed just by themselves. Also, you can customize the quantiles, right? If you need to see the 0.1%, the 1%, the 10%, there is a way to ask for that. And again, recalling part 1, we could find out exactly how to do that by typing question mark quantile. And it's going to show us, okay, we can actually provide a sequence of probabilities for the exact cut points that we're interested in finding out. And finally, here's a summary of the life spread, which we've already seen that. We can also do a histogram. This, I think, we're teasing you with a little bit of graphics before next session. So the histogram, again, a very simple command, hist. All right, so what other things might we want to do to study our data? We can create a table. in 157. This simply counts the number of observations, and in this case kind of just verifies that we have only 1 year of data. We've got one entry for each country, and they seem to be correct and complete. That's more of a verification step. All right, so in order to sort of simplify the way we look at this data, I'm going to create categorical variables. This is in line 160 and line 161. In line 160, I'm going to apply a conditional test. And the conditional test actually generates the new set of variables. So for those countries that have a greater than 5 gap, which is approximately the, let me run this one again. Right, our summary showed that the mean difference was 4.799. So 5 is close enough for this rough exercise to say if the country has female life expectancy is more than 5 years more than men, we're going to call that a high spread. And if it's less than that, it'll by definition be a low spread. So when I run that, the resulting variable generated by the assignment operator, and I had a typo there, is a true or false, right? So is it true that the life expectancy gap is more than 5, or false, or missing, right? And this is a logical variable in R, but we can work with logical variables very easily in R, as we're going to see. We're also going to create one for a high age. So the approximate mean of female life expectancy is 78. So if women live more than 78 years, that's a high life expectancy. Otherwise, we're going to classify them as low. And this is a little subtlety which can be important. When we attach the data, I skimmed over that briefly, and I kind of said that's a way to not have to use the $ notation to make a certain data set a default data set. What R actually does is make a copy of the data and kind of foregrounds it in the space. So if we make changes to the data, we have to attach it again so that the fresh copy includes the changes. So that's may seem like a little bit of a subtle caveat first time through, but you'll find out when you've tried to create a variable and it doesn't exist in your attached data set. I hope you'll remember that warning and you'll be able to come back and reattach your data. All right, so I have attached the data again. It gives me a warning that I'm actually overwriting all the other variables that were there with the new data. That's why we have this long statement to say the following objects are masked, because we have so many variables. And now we can create a table, right? There are 93 high spread life expectancy countries, 152 non. The high age difference is also similar kind of split. And when we do a crosstab, we just do a table of the two variables together in line 169. And that crosstab is shows us that 108, a big amount, fall into both the low age and the low spread category. 53 fall into the true category where they're both high life spread and high age. If these things were completely, related to each other, we wouldn't see anything on the diagonal axes, right, where they have a high age but a low spread, or vice versa. And this is the kind of thing that we can do a test to test the difference. We can do chi-square tests, we can do t-tests, and these types of tests, I'm not going to illustrate a chi-square test, but we're going to illustrate a t-test. That this is where R gets easy, because R is designed for statistics, and so once you know the name of the command, you just go straight to that And so we can say t-test, life spread. That's line 173. What is a t-test test for? Well, it's testing whether a particular number is different than a test value, right? Our null hypothesis. Now, by default, we're testing that the life spread is not equal to 0. Always the default null hypothesis will be 0. And we saw that even the minimum, there was no country in the world where men had a higher life expectancy than women. So we would expect this result with a minuscule p-value, super significant. We can definitely say it's not random. Women have a higher life expectancy than men. Now we could test other hypotheses by adjusting the mu, right? So if we say, is it true that women have a greater than 5 additional year life expectancy than men, we can adjust that. The mu is the notation here because mu is the Greek that's used for mean in the t-test. This is an example of R being like a little inconsistent, like each function is a little bit different. So instead of saying mean equals 5, for this test we say mu. And again, sometimes you have to use that question mark to make sure, okay, I remember how the t-test works. How do I specify the mean? Well, this will remind you that it's mu. And it will also show you the other methodological variations that you can use. There's always these sort of technicalities involved in the statistical tests, and if you need to adjust something specific, like here the equal variance assumption can be important. Those technicalities are there, and you can adjust for them in R. Just look at the help. Here we're just changing the mean to 5, and on line 174 we run the test again, and we do not have a significant p-value, at least if we're using the traditional 0.05. We can also see the confidence interval, that the 95% confidence interval includes 5, which is a little unusual, but in this case the p-value is still not significant. We can also change things like the confidence level. We can say with a 99% confidence level that the true mean is not 4. It's definitely different than 4, whereas we can't quite say it with the same certainty about 5. We also have this variation of the t-test where we can take a 2-sample t-test. We can compare 2 groups. So we have a categorical variable, which is high age and also life spread. It would not be interesting to test life spread against itself, but we can test whether life spread is significantly different between the 2 age groups, the high life expectancy women and the low life expectancy women. And that's in line 179. Oh, and I didn't run the entire line, so I just got this weird result. So here's our 2-sample t-test. P-value is highly significant. The true difference in means is not equal to 0. And here that's an appropriate assumption because we just want to see if those 2 groups are different. And difference in this case means having a mean that's not, that we can with some statistical certainty say is not equal to 0. And so we find that the low life expectancy women, that's the false group, have a difference of I'm going to round it to 4.4. The high life expectancy group has a difference of 5.4. So, it looks like a big gap. There's an additional year there in extra female life expectancy, but we can verify it via the t-test. You can consult the help for chi-square test. That's easy to run, very easy to look at. And so our last topic that we're going to touch on here is the statistical is linear regression. And so we'll be done in about another 5 minutes here. Linear regression is just LM. Now, like everything else in R, if you need other forms of regression, GLM, logistic, it's all there. There are slightly different functional forms and packages for that. I'll discuss a bit later, like how to investigate packages. I may make that like a separate video. But for just basic linear regression, you type LM, and on the left-hand side of the tilde sign, again, the tilde, I tend to view that as like as a function of, right? If I say like life spread as a function of GDP per capita, means I'm taking life spread as the dependent variable and GDP as the independent variable. The other terminology that you use is like the response variable and the explanatory variable. So life spread is response, GDP is explanatory. And then I can just run that, right? Again, I don't need the long notation because I've attached the data set, so I just use the variable name. And here's a odd thing about R is that when you run a linear regression, the only thing you get by default are the coefficients. And that's often really, typically we look for significance first before we even study the coefficients. So that's a bit odd. I'll explain how to get around that in just a moment. We have on line 190, we have the linear model without an intercept. If you need to not have an intercept, you use -1, and then we can just get a coefficient by itself. I'm not sure, that's probably not appropriate in this regression. And we can check other relationships, 193, 194. So we can see that fertility rate has a negative relationship to the life expectancy gap. Fertility rate has a negative relationship to GDP per capita. Higher income, less fertility. Life spread has a positive relationship to GDP per capita. So higher income means higher life spread. So we saw those basic relationships, but we need to know if they're significant. And to do that, it's illustrated in line 198. We use a summary command. So summary command is very versatile. Here's another example of how it's used. Inside the parentheses is our regression. So it's a summary of the regression of LM, And when we run it in this form, we get a more normal type of regression table. We get the significance on each variable. And here we find that actually it's not significant, at least in this naive form. Obviously, when you're really doing analysis, you're going to consider lots of other ways to formulate the problem, transform the variables, etc., etc. But we have the significance level, the estimate, and the standard error. We have the R squared, which is explaining almost nothing, and the other things that we typically look for. Let's see if any of those other ones are significant. So fertility rate is significant at a 0.001 level, and it doesn't explain a lot of the variation, but much more so than the GDP. And fertility versus GDP per capita also highly significant, with by the standards of this data set, a decent R squared. Okay, so we're just illustrating the basics of how this works. I don't want to read too much meaning into this data example. But if we want to, we've just regressed against one variable. If we want to regress against multiple variables, very simple. Just add them with a plus. Oh, what have I done? I have cleaned my workspace. I accidentally hit this little broom, and the little broom just wipes out the contents of the console. So if this gets cluttered for you, you can clean it with the broom. So where was I? So I was here. And these are all significant at the 0.001 level when I use them together. So fertility rate is explained by both per capita and the life spread in this example. All right, so a final power aspect of R is that a lot of stats programs will just give you this output. But R is, it's a system for statistical analysis, and it has these programming aspects. So we can store the data from a regression as an R object. And that's what happens in line 206. Instead of running the regression just in the console, we assign the regression to a named object that I'm going to call reg output. And now reg output exists in our environment, as you can see at the top right up here. And if I look at the names of reg output, that's the variable names, I have coefficients, I have residuals, I have fitted values, etc., etc. It's all been stored. And I can treat them just like any other R object. I can say, show me the residuals by saying reg output $residuals. The residuals variable in the reg output data. And here they are, just a list of residuals. Now, if you think about how you could use this, is you could run multiple regressions, 50 different versions of a model, store them as reg 1, reg 2, reg 3, and then start doing this subsequent analysis on specific things like the variation among the predicted values, or there are really a lot of possibilities with that. So this is an important feature, that it's not just printing on the screen, it can be stored. We also have all these quick functions that are easier to use if you've stored your regression results. So you can say predict, that quickly shows you the predicted values, which then could be plotted into piped into a plot. Analysis of variance, so ANOVA. If we need that particular table, we have a quick way to generate that. And we also can do things like, backing away from regression for a second, we can do things like correlation. That's in line 219. When we just run the core command, we're asking for the correlation between two variables. This is another case where we have to remove the unused data. So I want to say na.rm equals true, like we have been doing before. That also gets another error. This is yet another example of R being inconsistent, right? So the core command does not use na.rm equals true. It uses a different thing called use complete observations. And once we specify that option, it'll now properly generate a correlation for us. That's a case where you run something, you get an error, you go and look at the help, and you figure out how you need to modify it. This is a very typical in R. And 224 is, we can also do a correlation test to discover the significance of the correlation as well as the actual correlation value. So there's two ways to do it. One is just core, which gives you the simple correlation. The other one gives you core.test. And the absolute final thing for this part is we can plot our regression output so that we can easily diagnose whether the fit is good. This is built in. So we just say plot reg output, and it says down below, once we start that, it says hit return to see the next plot. So we do have to hit return, and then we'll start to see actually a sequence of 4 different plots that are typical things you'd look at to assess the fit of a model. So with the regression example, I tried to show you that using the function names for statistical things are simple. The basic way to use them are simple, usually just specifying a couple of variables. But the other options, the power options, are there. We can specify additional options. We can get the plots. We can store the results. All that is available in R. So that's kind of a basic view of data analysis. In the subsequent sessions, we're going to focus on plotting and data manipulation. And other data analysis focused around specific techniques is not something that's I'm going to do in the 2020 series, but we do have some older videos on that, like survival analysis and time series analysis. So let me stop here. I'll say thank you for listening, and good luck with exploring R.